So good evening, everyone. We have our panel for today. Panel 2 is on AI could solve the world's healthcare problems, and that too at scale. I'm the panel moderator. I'm from Purdue University. My name is Shumali Chatterjee. These are our panelists, as you can see. Dr. Manish Gupta, Dr. Amit Sharma, Dr. Dave Kotz, Dr. Amarnath Gupta, Dr. Anand Sivaraman, Dr. Sriram Kannan. Oh, that's the empty chair. I guess he's on his way. Dr. Monisha Ghosh and Dr. Gautam Shroff. This is the overall format we'll be following for today's panel. They'll have elevator pitches about 2 minutes each, followed by the presentation for about 6 minutes. I say about just to be polite. The rest is 20 minutes for Q&A. So a little bit of a brief foundational slides from the moderator. So I think machine learning, we talked about, machine learning versus AI. Of course, everyone knows that. But algorithm-wise, you can think of machine learning as being one of the foundational technologies. And in machine learning, I think deep learning, this is the right kind of climate for deep learning, where you have lots of data and lots of compute. Evolutionary computation has also been used. We heard a few talks today on scalable genetic algorithms. Another aspect in the healthcare arena is interpretable ML. So that's something that is very important to this domain. So if you can even have a less accurate algorithm, not necessarily, but at the cost of having a more interpretable algorithm is something that is preferred by both experimentalists as well as clinicians. The other thing that you see in this domain is you might have lots of features and not enough samples, so large P and small n, and that's where the powerful priors are helpful for the posterior inferencing. So this is on the foundational algorithmic side. Of course, you have other kinds of algorithms other than deep learning, but deep learning is helpful because the large volumes of data. In some sectors of healthcare, you don't have as large a volume of data. In those cases, simple support vector machines, et cetera, may work. On the compute side, of course, you have lots of different kinds of accelerators that can be used. So for CNNs, for example, you have a lot of matrix multiplication. So you have GPUs. If you want more flexibility, you can have you can code in FPGAs, OpenMP as well as MPI for scale up. When I say scale up, it's across the cores versus horizontal scaling or scale out across the different nodes of a cluster. Also, you have the frameworks for scalable computing such as Apache Kafka. And finally, cloud versus edge computing, right? In some cases, low latency is an important requirement. So you can think of yourself being in the doctor's office and you have some kind of video streaming. Of course, you don't want that to go to the cloud and come back. So maybe some kind of edge computing deployment may be helpful in scenarios like that. Now, what are some of the challenges? I myself work with metagenomics data, and there is this big repository called NGRAST and metagenomics. It's centralized right now, but we've seen there are advantages to federating some of these resources. So it improves, decreases the need for having these huge computational powerhouses centralized in one specific lab. And of course, lab is having to bear the costs of computation. It's not free. So federation can be helpful, and there are ways in which you can federate some of these production level resources. The other thing is privacy. Privacy is very important in this domain, and of course the industry has taken note of it. DeepMind, for example, has this verifiable data audit where it is designed to allow partners to check who has access to the data, when, and why have they accessed the data, right? The other thing that people don't think about a lot is computational sustainability. So I think that is something that people should think about as you have lots and lots of data. So sometimes these approximate modeling might be good enough, and you might not need as much compute, so that is something to think about. Sometimes you don't need these fully connected networks, so you might have better learning architectures. And what are the ways in which you can compress some of the data sets, So those might be some of the ways in which you can make the computing more sustainable. On the other side, of course, we hinted about this in the earlier slide, how do you deal with the curse of dimensionality? So lots of features, fewer number of samples. So one of the ways in which you can deal with this is the priors that are available to us. And another bottleneck here is heterogeneity, right? So as you have newer and newer instrumentation, the error characteristics, for example, change in sequencing instruments, for example. So these are some of the challenges that I could think of. Of course, our panelists will tell us more challenges and, importantly, how to surmount some of these challenges. So I found some startup, this is of course a smattering that I found of innovations in India. I'm going to stop here for a second and let you look through them. If you have others to add, feel free to add to them. But I think Healthify Me was a nice one where, they tell you what are some of the lifestyle changes that are amenable to your particular lifestyle and your particular, I guess this is something that you want to do, match your genomics and your lifestyle and see what are the kinds of changes that can bring about disease prevention. The other thing that Google is doing is they are teaming up with Aravind Eye for early stage detection for diabetic retinopathy, because early detection is a big thing here. So early detection is a big thing in lots of different kinds of cancer as well. So these are some of the startup innovations in India. Globally, we have seen some of the frameworks. They have started having a specific sector for healthcare. For example, sentient AI, digital reasoning. These have different forms of scalable computing that can be applied to healthcare-based data, whether it be genomics data or whether it be electronic healthcare records or other kinds of imaging data. So these are some of the sample innovations that I found globally. Again, this is a smattering of innovations. So how is AI being used in healthcare today? It has been found that only about 37% of these healthcare leaders, they use AI. And a little bit counterintuitively, most of these applications are in clinical use cases rather than in financial use cases. Again, another bottleneck that I found is trust was a big thing. So can you trust this AI? So more than 1/3 patients say that they won't trust AI. So that is something we might have to surmount and bring in some trustworthy frameworks and algorithms that bring in this important factor of patient trust and also a physician trust on being able to trust the predictions of these algorithms. So I think interpretability may have a lot to do with that trust. So they are sort of connected to each other. So these are some of the guidelines I gave to our panelists. Of course, they can get creative around these or totally disregard these, but these are some of the things that you can keep in mind. I think one important thing that I found this MIT study where, AI cannot replace the doctor's gut instinct. Maybe people who are working with effective computing or sentiment analysis may have a way to surmount this. But do we really need to surmount this? Do you not want to go to a doctor when you go to your doctor's visit? Are you going to be happy to see a bot? And so, things to think about and mull about. Something closer to my group is we work on genome annotation tools. So how can you integrate multi-omics data and make disease predictions for both complex diseases and also rare diseases, right? So different challenges there. And finally, this is the Watson medical algorithm. This is just from XKCD. And, this is more complex than what your grandmom learned to code out. So you want to have interpretable, easy recipes and not mind-boggling, cumbersome recipes. So I think with that, this is our timeline. And I will have our panelists give their elevator pitches, which is 2 minutes, followed by more formal presentations of 6 minutes by our panelists. So we will start with Dr. Manish Gupta from VideoCan.
So what I would say is, it's a very exciting area because healthcare is pretty much a broken system all over the world. If you look at advanced economies like US, which have this very advanced healthcare system, they're dealing with this huge problem of rapidly rising costs. Countries like India, our average cost spent on healthcare is still very low, but that's because much of our population doesn't have access to healthcare. And if you look at that subset of those of us, for instance, in this room, who are lucky enough to have access to decent healthcare, again, our cost curves are again very high, and it's an unsustainable curve because, if you wanted to provide healthcare to 1 billion plus people in India on that same cost curve, it just would not be sustainable. So the key to this, in my view, first of all, I don't think AI will solve the problem. The first and foremost problem is even a business model problem, that healthcare inherently, hospitals, healthcare providers have an inherent incentive to make you spend on healthcare. Which is contrary to what the goal is, to reduce the cost of healthcare while improving quality. So there have to be fixes in the business model, which, for instance, have been attempted through, for instance, Obamacare, Modi is trying to do this healthcare scheme, and so on. The other aspect is to make things more proactive, because things get more expensive in healthcare when you let problems remain active. So there's this famous saying, prevention is better than cure. It can be applied all the way to different tiers, as I'll elaborate later. if you can take more proactive action and you can actually reduce the cost of healthcare while improving quality. And that's where I think AI can play a very, very critical role. Of course, there are also many, many challenges that need to be overcome.
Yeah, I agree with the point of business outcomes. I just add at Microsoft Research, we've recently started looking at how AI and machine learning can be used in societal impact problems. One of them is healthcare. And the short answer is that, as Manish was also saying, AI is not going to solve the critical problems we have in healthcare. What it may do is that it can augment the capabilities that we already have. So what that means is that we already have a great private hospital. If you add AI to that hospital, it is going to improve services and also help the doctor make better decisions. But it's not going to magically create a self-driving doctor in a remote area in India. And the second thing, which I also say in my talk, is that I think it's less about AI and more about the healthcare processes and the people who are a part of our healthcare system that I'll talk about that really comes out when you want to solve challenges in healthcare.
So I'm David Coates from Dartmouth College, and most of my work has been involved in mobile health and wearable technology, and so most of my comments will probably be coming from that direction. And my take on this is not so much about AI specifically or ML specifically, but more about technology, wearable or otherwise, and how well it could or could not affect healthcare. And I think my views are likely to align with the others. Technology is really an enhancer of existing activity, and that could either be good activity or bad activity, so it can make, it really just expands what you're already doing. And so the careful application of technology could help with improving the cost, quality, or access challenges in healthcare. But the real challenge ultimately is to address the business processes and the fundamental human systems that deliver healthcare. And to the extent that technology can amplify the good aspects of those systems and make them more effective to either increase access in dealing with scale, reduce cost, or improve quality, great. But you can't focus just on the technology. You need to be looking at the holistic system view.
So my name is Amarnath Gupta. I agree with whatever has been said before. So there has to be a business case, and there has to be attention to what we are using AI or any technology for. I think part of the difficulty that we see is I work with neuroscientists, with geneticists, with people who are trying to design clinical intervention for problems of obesity, people who are trying to design matching algorithms for clinical trials. And the common theme is we talk about AI without deliberating on who my target audience is, who's going to use this. And depending on whether it's the caregiver, or it's the patient, or it's the doctor, or it's the person who is trying to advise patients on what clinical trials to go to, I think the actual technology and techniques you are going to apply would be different. And I think this target focus, the focus on the target audience is currently missing from whatever we are doing in AI research. The second aspect of what I'm going to talk about is AI research is great, but it's going to succeed if only we have more data for more parties. Currently, there is a serious shortage of the kinds of reference data that would be necessary for building models. And I think the marriage of AI and algorithms and data awareness should go together. That's not happening clearly. Similarly, there is a wide gap between the data integration practices that the database people do and the model building practices that the AI people do, and that gap needs to be bridged. Thank you.
Anand Sivaraman. I run a company called Remedio, which has been using AI and smartphone-based imaging as a means to create access to eye wellness. The perspective that I would want to bring to the table is actually the challenges we've seen and the successes we've had in finding out these business models that do work. Where in a 3-year study with Arvind, where we've now screened a reasonable number of people, the outcome is AI has helped enable a hub and spoke model that has actually made it convenient for people to get screened. So I'm going to be focusing a little bit on the use of technology in creating a screening network, which I believe is a lower hanging fruit from the business perspective, but I agree with the rest of the panel members that it's not a technology problem, it's at the end of the day a delivery problem. And how do you actually look at delivery within the lens of not only technology, but aspirations as well as business models. So a little bit of that is what I'm going to be talking about as part of the perspectives here.
Hi everybody, my name is Sriram Kannan. I'm an assistant professor at the University of Washington, Seattle. My background is in information theory and its applications in a variety of areas. The perspective I have is basically that when you think about AI in medicine, there are two broad ways in which you can think about it. And the first one, which I think most panelists have already addressed, is its ability to improve delivery and reduce costs. There is a completely complementary angle to the use of AI in medicine, which is to facilitate entirely new cures. Our ability to process molecular data at an unprecedented level is enabling the collection of immense amounts of data from a single experiment, from millions of cells at the molecular resolution. And one of the very important questions is how can AI help in facilitating scientific discovery, which can potentially lead to brand new cures, which are completely infeasible as of today. I think this is the angle I'll be talking about.
My name is Monisha Ghosh. I'm at the University of Chicago. And I come from a very similar space as Reena. My background is in wireless communication, signal processing, and information theory. And we had this very interesting work where we were trying to predict which patients in cardiac ICU were going to die because of something called acute lung injury, which is very, very difficult for even the most seasoned doctor to pick up in time. And what Mayo Clinic has always been at the forefront of work like this, and what they had started off with was collecting a lot of data on patients, not just the data when they came in, but their past history, how many times they'd been hospitalized, what medications they were on, what their family history was. And they really felt, they did not know for certain, but they really felt that all of this should somehow be able to help the physician in the ICU make the right decision as to what was going to happen to this patient in the next hour. And this was in the early days. We never even called it AI back then. This was 2010 or 9. And we found that very simple techniques would actually help the doctor a lot. Going back to what you were saying, it's not going to replace anything. It's going to allow the doctor to process huge amounts of information coming at her, like there's information's coming from the patient bedside monitor, there's information about tests being done. How do you process all of that? Recently, over the last 2 years, I came back to it at a different angle, which was looking at cancer genomics. And the two questions, and I'll talk about that we wanted to answer was, given how drugs have worked on certain genomic cell lines, and I as a patient come in and I have my genome sequence, can I as a doctor pick out what is the best drug that this patient should have? What combination of drugs would work best for this patient? So these are areas where, much as we would like to just use numbers, we need a lot of biology. And I wish we had more people with medicine or biology background in this panel to really round it out.
My name is Gautam Shroff. I head TCS Research. I've been working in machine learning for quite some time, and I don't know that much about healthcare and genomics, but I had groups which work in that area. So I'm going to talk a little bit about their work a little later on. But broadly speaking, many of the comments already expressed I agree with. Perhaps the only one I kind of disagree with is that technology can solve all the problems. I don't think it can. I think there are many problems which will require fundamental new understanding of human biology. I was talking to Atul Gawande a few years back. He's a famous surgeon, as you might know. And I asked him, to what extent can a doctor be replaced by a mobile phone? And his answer was certainly not 0 and certainly not 100. So somewhere in between, we don't know where. And being a networking audience, I think this whole business of access and getting access to healthcare is a very important part of increasing access, reducing costs, etc. But at the same time, let's also understand that, we don't really quite understand human physiology in the normal sense that we think we do, because we don't monitor normal people as a normal course of time. We monitor them when they're sick. So how does our blood pressure really vary throughout the day? There is no good model today, or pulse or anything. There is no, because we don't really monitor people at scale when they're healthy. And this is other problem with early detection techniques. Early detection assumes that somebody is going to get a test because there's something wrong. And it's immediately a sample selection bias comes into all such studies. Because you're selecting people there's something wrong with that person. So you have this challenge. And the third problem is, again, to do with trust. Even the most obvious computer vision mechanisms of automating radiology, which today are very clear. You can automate 90% of what a radiologist does. But radiologists are still there because of trust. And you just can't get rid of that, because it's okay to have 99% recall, but you don't want that 1%, especially if you're dealing with cancer. So you need 100% trust. And you just can't have a plane flying with 99% accuracy, right? I wouldn't fly in that plane, right? So this business of AI and mission critical systems is yet to be solved, and I'm wondering where self-driving cars will take us, but this is a serious problem. I think the biggest improvement from machine learning and AI is going to be in, as was mentioned, in finding new cures. Because the genome is too complex for us to actually explore it without sophisticated machine learning techniques. And in the end, we will need better biology to explain it and develop new cures. But that's probably where the biggest impact is going to be.
Okay, so on to the formal part. So I was talking about this problem of high cost, and there was a doctor who famously illustrated this problem by pointing out that, what's the most expensive place to stay overnight these days? So he said it's not the typical 5-star hotel in a fancy location, it's the ICU of a hospital, where you would spend upwards of maybe $10,000 to spend your night in that bed. So if you can, and actually there's so healthcare system is organized in the form of these tiers. And in fact, there's a more expensive tier, right, which is the graveyard. So what you can do is, by applying AI, you can try to do this predictive analytics and try to predict complications, before they happen, before I fall. Ideally, an AI system should just kind of save me. And all of these technologies today are still not very mature, because, if you look at commercial systems which are deployed, so for instance, when we were at Xerox, through the ACS acquisition, we had the system, and it was rule-based, put together by a combination of doctors and technologists, and often has too many errors. And as you start to put together models through which you can reliably do these predictions, there are a lot of challenges in terms of, often you don't have enough data available. And even after you get all of that data, there's this huge issues of, and all the noise in the data and so on, huge issues of class imbalance. That if you have relatively few people who are going to die or who are going to get that complication, and most people who are going to be just fine, even if your sensitivity is a little bit, if you have a sensitivity of, let's say, 96%, it looks great, but that 4%, the number of false positives you would get out of that 4% will hit you. It will be higher than the number of true positives that you're catching. So that leads to the problem of trust, which is why a number of these systems, for instance, deployed in hospitals, trying to predict which patients are going to be in an emergency situation, can you prevent them from having to go to the ICU, often these alarms, these are ignored by doctors and nurses because of this alarm fatigue, that the systems just aren't doing a reliable prediction. So to me, the very exciting thing is that in the future, we believe a lot of healthcare action is going to actually move out of hospitals. And for the networking audience, I think it's again an exciting thing that when we are going about leading our normal lives, at home, at work, and so on, we are going to be monitored. You're already seeing signs, right, of Apple Watch, Samsung Watch, all kinds of Fitbit, all kinds of devices through which your body vitals can be monitored. And again, I mean, we are very far from being able to really make intelligent decisions. As Gautam pointed out, there isn't even a lot of data about what is normal, because there could be variations that just happen in normal life. So I'll just very briefly talk about a few projects. So we had kind of, when we were at Xerox Research, projects along pretty much all of these different tiers. And of course, I mean, so essentially what you're trying to do is, if you're in the ICU, you're trying to prevent the patient from dying. If you're in the hospital, you want to prevent the patient from having to go to the ICU. If you're in the primary healthcare center, you want to take care of the patient right there and prevent them from having to go. And likewise, if you are at home, ideally you would like to monitor and warn them and prevent them from having to go to a healthcare center. And in fact, in many cases, even suggest kind of wellness kind of activities because a lot of healthcare problems are arising because of unhealthy lifestyle choices. So to provide a little bit about a few examples of how you could be monitoring things. One of the startups which you just mentioned, which was a spin-off of some work that we started at Xerox Research, Nirame Analytics. It's been known that when malignant tumors grow, there is a lot of, as they feed, there is a lot of blood vessel activity in the region to feed the tumors, and that shows up in the form of a thermal signature. So it's been known that actually through thermal imaging, you could actually detect these tumors well before mammography could. But yet the medical community gave up on all these methods of screening in the 80s because there were too many false positives. So now the question we raised was, can you apply AI? And as you look at various kinds of thermal images, can you now utilize AI to reliably distinguish between malignant and benign tumors? So there is interesting work. So I'll stop with and likewise, we were using cameras to monitor, and one very interesting piece of work that was done was, can you use a simple webcam to detect the respiration rate of a baby? And one of our researchers said, look, under certain conditions, I will give you the exact algorithm. If the respiration rate is perfectly periodic, then instead of taking all these pixel values and then averaging them out and so on, I will discriminate between those pixels which are showing that perfectly periodic motion and those which are not, and look at those two. At the same time, finally, I don't have time to go through these. There are a huge number of outstanding challenges as you try to really have real impact out of all of these techniques. People have already talked about data, accuracy, and so on. So, okay, I'll stop here. That there are still, apart from the challenges within AI, there are also other challenges like behavioral science and so on to be able to figure out how to influence humans who have to make those decisions, whether those are doctors or patients. So I'll stop here.
Hi everyone, my name is Amit Sharma. I'm a researcher at Microsoft Research. And in the past 1 year, we've sort of looked at how we can use cloud and AI technologies for societal impact. And we've started a number of projects, and also we're looking at how AI can be used in previous projects. So I'll just give 2 examples that I've been working on. So the first one is 99 Dots. It's a solution that Bill Thies and other researchers in our lab built for adherence in tuberculosis. So as many of you might know, tuberculosis is a disease for which you have to take antibiotic medicines for 6 months. And if you miss some doses, then the bacteria becomes resistant, and then you have to take much harder antibiotics, right? So what we developed was a very simple solution, which was that you can give a missed call each time you take a medicine, and that helps doctors and health workers track who is taking the medicine and who is not and who needs more health resources, right? So one learning is that this technology has worked, and it's a very simple technology. But how AI can help is that now we can look at the data that simple technologies produce, and then maybe predict, can we predict before a person is going to miss medicines? Can we help the doctor or health workers find that out in advance, right? Another application that I worked on is in a separate domain, which is mental health. And here too, even in India and other developing countries, there's an increasing amount of people who are suffering with mental distress. And because of less access to psychiatrists and psychologists, they can't really just go to a professional, right? And so they go to these online forums. For example, I have a screenshot from TalkLife. And here too, we find that using just very off-the-shelf machine learning techniques, we can detect conversations that might require more support, right? So you can now imagine clinical psychologists only intervening in conversations where people are, for example, here talking about self-harm. So that's one side of the story, right, where we have technology and AI where we can just use predictive methods to do these early warnings or early sign detection that helps. The other side is in prevention, where my colleagues in Microsoft in Hyderabad have also worked on just looking at, can we predict early warning signs of cardiac illnesses or other kinds of problems with the heart. And here too, you find, and we have great promise, that these kinds of techniques can be used to predict bad things before they happen. Right? So overall, I think I personally have a great belief that there's immense potential for AI technologies to be used, especially in situations where you have sort of simple prediction problems with defined inputs and outputs. And the way they are going to be used in practice, as we've also seen in these examples, is always to augment what people are already doing. So if we already have health workers doing it, this is not going to replace it. It's just going to help them do their job better and hopefully serve more patients. And the vision that this entails, right, not today, I don't think AI is ready yet, but the vision is that how it works is very simple, like a monitor that doctors use, right? So if you go to a hospital and you have this pulse monitor, you trust it, you know exactly what it's doing, and it shows exactly what it's doing. And it beeps when there's a problem, and most likely there is a problem, right? So Manish was also talking about trust, false positives, whereas what we have right now is some complicated network which has yet to reach those levels of standards that machine learning, medicine requires. So I'm just going to talk about three things that in any healthcare are the three sort of topics that you have to look at. One is prevention, diagnosis, and treatment. I'm going to give a quick summary of where we are in state of the art and what still needs to be done if we have to really use this in medical settings. So in prevention, as I've also given examples, ML systems can help detect early warning signs. That's really good. In diagnosis, we can help decrease times of diagnosis. So people talked about radiologists. This also happens in pathology, where if you're given clean images or videos, we can actually reduce time of diagnosis. And finally, treatment. There's still ongoing work. We can sort of give treatment advice for some very simple cases, but in general, it's a much harder problem, and I don't think we are there yet to say much about it. But even in the first two, there are these key challenges that I hope we can discuss in the panel today that need to be solved before we can think of clinical uses, right? So in prevention, the obvious question, let's say a doctor tells you that you have an 80% chance of a heart attack in the next 2 years. What's going to be your next question? I mean, you would want to know what can you do to reduce that chance, right? So that prediction by itself is not that useful, and current techniques do not have that causal interpretation or even sort of counterfactual analysis of what you can do to improve your chances. Similarly, in diagnosis, people talked about explanation or interpretability. This is sort of a constant struggle between the two things, and there's more work now that tries to be more interpretable. And finally, in treatment, as I said, it's a much harder problem. Hopefully, in the future, the AI community will come together and we'll have better solutions for actually recommending treatments and not just prediction. Quickly, you can read through the possible futures, but really, we're going to have more adoption in diagnosis cases with well-defined inputs like radiology. And we'll also have more adoption where alternatives don't exist, right? But for other problems, research still needs to catch up to match a good doctor in a good hospital. I'll end with that.
Okay, so and I'm David Coates, and like I said earlier, my interest is really more in technology, digital technology, not just AI, not just machine learning, and it has the potential certainly to help improve the quality of healthcare through the kinds of examples that people have already mentioned. It can extend the reach of healthcare to deal with the challenge of scale, and particularly in a country like India. And it has the potential to deliver preventative care, to encourage wellness. And most of the conversation so far has been around diagnosis and treatment, traditional healthcare. My interest actually tends to be skewed towards healthy people who are generally well or who have chronic conditions who need, for example, obesity or diabetes, where ongoing maintenance is really the challenge. So one of the key points actually is something that I've derived from a book that I just read, Geek Heresy, is that technology is an amplifier. This is something I mentioned earlier. This book was written by Kentaro Toyama, who was at Microsoft Research, Bangalore, and actually with me co-founded the NetHealth conference several years ago. And it's a really great book, by the way. I would encourage you to read it. And his point ultimately is that technology amplifies existing trends or behaviors in a system. And if those behaviors are good behaviors, then technology can help improve and amplify those goods. But if it's not a healthy system, as it were, then it can actually make it worse. And the key to effective change, if the goal is to change, in this case to improve or solve the healthcare problem, right? We need to adapt systems that are for existing systems for health maintenance and health recovery using technology. And so my interest, as I said, is more in the mobile and wearable health technology, where sensors are used to somehow collect data either about the person or about their context, social context, behavioral context, health context in general, and then you use machine learning classifiers to infer physiological or behavioral or contextual factors that somehow relate to wellness. And then the challenge, of course, as others have mentioned, is where do you get the data? So we need to collect data from a lot of volunteers. I'm surprised nobody has yet mentioned precision medicine or, for example, the All of Me project in the United States, where they're enrolling 1 million people, a million representative sample of Americans, and the goal is to collect years of data from 1 million people and then use all of that through AI and machine learning technology to do prediction, diagnosis, treatment, and eventually personalized, customized to a single individual treatment, including pharmaceuticals. And then the classifiers have to be evaluated, but not just in the lab, but also in the real world. And the challenge we have today in mHealth and other is in actually validating these things in free living conditions. I see a lot of potential in digital interventions using apps or other devices in free living conditions outside the clinical setting on people, and then using something that people are now calling JEDIs, or just-in-time adaptive interventions. You sense the context and the behavior and the physiology, and then you adapt the intervention in real time to whatever's happening in the person's life so that you can hopefully change their behavior for the better. The challenge for all this promise, all this potential, is actually to validate them. So there's a ton of technologies, there's a lot of papers, a lot of academic papers. I tested it on 20 people. They were all grad students in my department, and look, it works, 98% accurate. The problem is when you send it in the real world with real people, with thousands of people, does it really work? And so in order for us to actually make healthcare systems change, we need high quality, randomized controlled trials and other scientifically founded evidence for these technologies. Thank you.
Okay, so I was more of a good student and tried to follow some of the questions given to us. But before that, so there is, I'm intrigued by the kinds of infographics people put together. So this is one of them, right? So this has the flavor of, oh, isn't life wonderful? AI does so many things. Well, that's great. And it's not all wrong. Like all of the other panelists have said, there is indeed a lot of activity in terms of the number of companies, the number of technologies, the amount of adoption we are seeing in pockets. But given all of that, what I want to talk about is some key missing pieces that I think should be there for AI to actually work. So these are the questions. The context of my presentation is essentially this. So when people design clinical trials, the idea is to find, so you have a new drug or you have a new intervention and you're trying to find people who would match the requirements for that. Now that's great, and the way it's usually done is the clinical trial, the company who came up with the drug essentially appoints a bunch of physicians, typically at very reputed hospitals, and these physicians have their own patient body, and these are the people who get enrolled. The goal of N of 1 is what are the other people who do not normally have access to these physicians? Can we target those patients and who may be one of a kind, maybe they are in a remote place or they have a very rare conditions, how can you take clinical trial to them? Now, if we want to do social good, reaching patients who need healthcare is an important thing. So typically, in this N of 1 goal, you would have a patient who says, I have such and such symptoms, I was just diagnosed with pancreatic cancer, and I need to find the right clinical trial. So what would the person do? We'll go to the web, and given a bunch of clinical trial portals, they would try to see if there is a matching clinical trial. Now, lo and behold, let's just stay on that step for a second. Here is a person who is trying to say, I want to get to a clinical trial, can I find the right one? Now, usually, it doesn't really work like that. So the specific example is I have some work with the Pancreatic Cancer Advocacy Network in the US, where I have there are a bunch of people, they're all volunteers, most of them are volunteers, and patients call them and say what they have, and these people advise and set them up with the right clinical trial. That's what these people do. The amount of time spent by an average person with one patient at one time varies between 90 minutes and 2 hours. Because the patients are not necessarily eloquent enough to give everything, so they have to get the information from them. And after that, they have to match it with whatever the clinical trial documents say and mentally map the patient to the trial. Now, if you look at the trial, the clinical trial document has two things called inclusion criteria and exclusion criteria, which are typically text. They look like this. And if you look to them, they're hideous. Somebody cut and paste stuff from the clinical trial protocol, and with this, the person who is trying to match is trying to map this to whatever the patient is saying. That seems like a case where AI should be able to help for two reasons. A, the person needs to parse through all of this to see if there is a match, and therefore the number of patients a person can work with on any given day is really small. This number needs to increase if you want to reach more patients. So what's the problem here? The problem is the NLP technology. There are two kinds of problems. A, do I have the right NLP technologies who would read these things and figure out exactly what criteria are specified so that they are machine processable? And B, the people who produce them, can we have the infrastructure so that the specification of a clinical trial protocol is made in such a way so that AI algorithms find it easier to work with? So we have two kinds of infrastructure problem. One is research with NLP. The other is production of the right kind of data that helps the matches. And currently, none of these things are happening because these guys are not necessarily talking to each other. Okay? Role of medical practitioners is actually the ecosystem. So we talk about the people, the point of delivery, and I think the biggest thing that they can do is figure out how to evaluate the technologies of AI. How about the beneficiaries? I think I'll stop with this. The most important thing is there is not enough data, for example, in the genetic variations in India, to see what the genetic subpopulations have with respect to family history, disease proclivity, and many other characteristics, so that the AI algorithms can create models. There is not enough data to create models, and it's the patient's responsibility. If AI has to work as an infrastructure, the patient community and the beneficiary community has to come up and supply their data, privacy pending, so that this can be done better. And technology inflection points, oh, there are so many. One big one is that the data management work and the AI modeling work do not seem to come together. They need to come together in terms of research. Thank you.
My background is more of a chemical engineer. I finished my engineering at MIT before I moved back to India to work at the intersection of technology and public health. So, to this question, I think medical imaging is one area where a lot of the points that were made in diabetic retinopathy, for example, we know what is normal. We have data to show what normal retina looks like. We know what the different stages of disease look like. So it's a well-defined problem. So oftentimes it's important to look for well-defined problems for a new technology to sort of ask, can it actually cause an impact there first before we start looking at it in terms of scale, in terms of much bigger public health problems. So to that extent, what we've been focused on is to look at retinopathy screening, but this as a business. The intent is not only to stop at research, but to ask the question, how do we do this in order to be able to create this as a sustainable business model to create access and therefore prevent blindness. Now, what we have is a device, because it's not about the AI solution alone. It's a smartphone-based device that allows you to take high-quality pictures of your retina without needing any dilation of your eye. And you have an edge-enabled AI that runs and identifies whether or not you have lesions in the eye that may warrant a specialist referral. Now, what's happened in terms of converting this into a business model is you actually have FDA, which has stepped in as a regulator to define the clinical endpoints at which you're doing as good, if not better, than a group of specialists looking at the same images. So to the question in terms of 99% accuracy on a flying plane, if let's say you are able to do as well, if not better than any other plane that you're flying on, is I think the analogy. So there are FDA mandated superiority endpoints that all of us have to meet, which in a way then sets the bar in terms of what's acceptable. So I think those are sort of the rules beyond, let's say, the mathematical frameworks that are important to look at. Now, I think the next part that's really exciting to me is to ask the question, can such health screening opportunities be extended to other forms of imaging? And what do I mean by that? We've been working for 3 years with Arvind Eye Hospital, and we've screened around 25,000 patients, and there was a 3 times increase in the number of people that actually went to seek a specialist referral as a result of them being told that there are changes that they otherwise have not known. It taught us some things in behavior as well. We as Indians, even if I were to ask this group how many of us have actually gone and taken a test to know whether we are diabetic or not, chances are not many of us are. But we made it convenient for them to get tested. We said, okay, what if we place these in centers where it's easy for you to get tested? It's interesting, even as we were having the demos out, we had many people who wanted to get it done because it's easier to get done. Hey, I don't need to go to an ophthalmologist, can actually come and get it done. So I think there is a behavior psychology in terms of promoting health-seeking behavior as a result of many of these technologies. And I'm sort of grouping them in the medical imaging space because of the fact that normalcy and biology is very well elucidated in that space. What gives me a lot of hope is, can we empower the family doctor who now can actually be able to use technologies like AI, ML and devices, because the way you interrogate is as important as the way you interpret the data. And is it possible for us to be able to empower him to be the first point of contact for anyone that actually needs attention even before you go to a specialist? So we've been working with the government of Kerala where we brought these devices to the public health centers, and we're not alone. There are quite a number of groups that are starting to do it. So I believe that there are going to be challenges, and a lot of these are related to what we have already talked about. I'm not going to be focusing a lot on these, because this is on the tech side, which we've all agreed is doable. I'm going to be focusing on the business side, and this is very important, I believe. We are not the only company in AI that's in this space. But if you were to ask a company in the US that's working in AI and diabetic retinopathy, for example, the cost per report is actually based on the efficiency of the CPT code associated with the reimbursement that goes to an ophthalmologist there, which is around $17 to $25. So therefore, they price it at around $7 to $8 or $9. In India, a good vitreoretinal surgeon charges 100 rupees or less than $2 in order to give the same quality output. So I think it's extremely important to ask what are the right business models by which you bring such technologies to market. And that's been a lot of what we have to focus on, because we need volumes. For volumes, you need to promote health-seeking behavior, because screening is possible only if you promote health-seeking behavior. And therein lies a lot of the challenges, but I remain upbeat because out of the fact that we were able to screen a certain number of people, the fact that we increased by threefold the number that actually was saved from debilitating blindness as a result of them being able to seek a specialist care, does seem to indicate that we may be able to use these technologies, not in all forms or not to sort of claim that you're now going to, this is the panacea that is there now for healthcare in India. But there are very well-defined problems where you may be able to bring it to bear, where I believe data is available, and that's one of the reasons why you would see Google and everyone else working with groups in India, because we do have data. But the problems that are associated in terms of building publicly available databases, these are things that we as device manufacturers have also started getting into, which is, can we build consortiums in order to be able to create high quality de-identified data that is open source and is shareable? Can we start looking at AI ML that requires low data approaches? On the hardware side, it's not enough that you take the same devices that are available in the hospitals to send it out. So those are some of the innovations on the hardware and devices side. I leave the rest because the rest is technology, but thank you so much. I wanted to just share these as perspectives as well.
The way I think about AI in medicine is that there are really two fundamental roles that AI can play. And the first role, which I think other panelists have touched upon quite eloquently, is how it can reduce the delivery costs in various applications. So here are some examples from the University of Washington, from some of my colleagues at the Ubiquitous Computing Laboratory, where you can try to bring smartphones to do various types of detections. The SpiroSmart is an app which can try to detect lung performance. You can do jaundice monitoring using a camera. You can try to do hemoglobin measurements using smartphone cameras. These are examples where you can try to use smartphones and technology along with some AI backend in order to reduce cost. However, what I'm going to talk about mostly is the second aspect, which is how can AI really enable novel cures for diseases? And it is a very tall order to claim that indeed AI can do this, but if we take AI as not artificial intelligence, but as augmented intelligence, where it can help us as scientists and in doing these discoveries. So I'll present here some of the enablers for doing this. And from the biotech side, I think there are major enablers. And I'll talk about two of them. One of them I call better observational ability, which is the rise of new methodologies by which we can interrogate biological systems at the molecular level. At the same time, and equally important, is better interventional ability, which is the rise of new methodologies by which we are able to intervene equally efficiently at the molecular level. And the AI enablers, which are also playing into this ecosystem, are how do we extract signal from noisy high-dimensional data, and NLP and computer vision, which I'll touch upon. So this is going to be a biased sampling of what can be done in this area based on my own personal experience. Okay, so in better observation, I'm going to point out two major breakthroughs in recent times. Many of you may have seen this figure. This is how much does it cost to sequence a human genome? And there has been major breakthroughs in our ability to sequence the human genome over the last several years, decade and a half, and the price having fallen over 6 orders of magnitude. So even surpassing Moore's law in its efficacy. So this is our ability to sequence a given DNA sequence. And there are many interesting computational problems that arise out of this technological breakthrough. For example, the sequencing methods only sequence short fragments of DNA. How do you paste them together to actually reconstruct the entire DNA? Another example of this is in taking, an ecosystem that has spun out of this ability to do DNA sequencing very efficiently is the ability to integrate other molecular attributes using DNA sequence as an intermediary. For example, can you sequence RNA? Can you sequence the 3D structure of the DNA? Can you sequence how proteins bind to DNA? All of these new questions can be answered by basically converting the biochemical measurement into a DNA sequencing measurement. And one example is RNA sequencing, where you not only want to monitor what your genetic component is, but how it's getting expressed in real time. The second enabler from the biotech side is not only that these measurements, the ability to measure DNA or RNA that we had over several decades, but also now you can measure them at the single cell level. What do you mean by that? Normally when you do DNA sequencing, you extract DNA or RNA from a bunch of cells together, called bulk sequencing. And from these bunch of cells, you basically take the extracted DNA and sequence it. However, when studying a variety of problems, what you want to understand is the heterogeneity in the cells that you're collecting. For example, inside a tumor, different cells are actually having very different sets of mutations. So the ability to do single-cell DNA and RNA sequencing has tremendously enlarged our ability to understand what is going on. And what this has done is, for the first time, it is impossible to do biology just by doing a simple intervention and observing, which a biologist used to do. Now you run a single experiment and you get a terabyte worth of data. And we need intelligent analytics methods to actually work on them. And what do I mean by interventional ability? And one of them, as many of you may have heard well, is the CRISPR-Cas9 system for gene editing. And the ability, the sequencing has provided us an enormous ability to read biology. But we also need the ability to write biology. And that is really afforded by the CRISPR-Cas9 system, which is essentially a method to go and rewrite whichever portion of the genome that you seek to do. And similarly, we also have an ability to edit DNA at the millions of cell scale. So there's a new technology called Perturb-seq, which essentially lets us edit DNA at a cellular resolution. I'll just quickly mention the role of AI in this. And when I said, can AI give rise to scientific breakthroughs, I think it's very important that we don't think of each experiment in isolation, but stand on the shoulder of giants, on the literature that has been collected over the many decades of biological research. And here, there is a very interesting interface between NLP-type techniques, which can extract data from the collective history of our scientific literature, and causal inference, which you can do now that you have both observational and interventional ability. I'll stop my presentation with that. Thank you.
So while I'm waiting for my slides to come up, let me ask you a question. How many of you took at least one flight to get here? Okay. How many of you really looked into the background of the pilot who flew you there? How many hours of flight training they had, how many incidents they had in their record, anything about the background of the pilot? Nobody. How many of you would choose a doctor that way? Nobody, right? You would? You would just choose a doctor out of a book without finding out? Okay, right? So this example was actually told to me many years ago when I did my first project in bioinformatics with Mayo Clinic. And what he pointed out was that flying was really dangerous when you relied solely on the expertise of the pilot. It was only when you had autopilots come in, when you had all of the aids that came in to flying, that it became a much safer thing. So this goes into a little bit of the trust issue that was discussed earlier, that people are not going to trust an AI model as much as they trust a doctor. And the question is, what is the root of that? I mean, I'm not going to really get into that question, but it's something to think about as to why is it that we would trust one person's intuition or experience more than a system which could potentially garner the collective wisdom and collective experiences of a large number of doctors, right? Maybe it's not really a technical problem. Maybe it's more about how we behave as humans. Anyway, let me I just have a few slides that are going to talk specifically about a project that we're doing at the University of Chicago. Okay, where we are looking at cancer genomics. This is a project at Argonne, University of Chicago, and the National Cancer Institute, and NIH. And there are two questions that we're really trying to answer there. One is personalized cancer treatment. This goes to the personalized medicine question, is can we use sequence data that we have? And I will talk about where this data is coming from, which has been run on a bunch of different drug molecules to predict which drug should be used for a particular patient. So you come in as a patient, and we sequence your genome, assuming that the cost of doing this has gone down significantly. And then I run it against the data that I have of drugs that have been run against a bunch of genomic sequences to pick the one that would work best for this particular patient. It's a much more difficult problem than it seems, actually. And then the second question that we were trying to ask is drug synergies. So many times what people have found is that two drugs may not work very well individually on a particular cancer, but in certain combinations of drugs work much better than others. Now it turns out that there are tens of thousands of drug molecules that have been actually tested, FDA approved for cancers, and it's not really possible to take all pairs of drugs and actually do wet lab testing on them. So the question is, can you take a small set of data that you do have of drug pairs and then try to predict which drug pairs would be beneficial, and then a smaller subset of those could then be actually tested on tumors, on mice models or other models to figure out whether that works. So those were the two problems we were going after. Now, what is the data that we used for this kind of work? So there is the NCI 60, this is the National Cancer Institute 60. These are 60 cell lines, so these are synthetic cell lines that I think in the early 80s that were developed, tumor cell lines for which the sequence data is available. So these are, I think, 6 or 7 different kinds of cancers. So as you can see, it's not a whole lot of data, right? But it is very good data. It's curated data. We know for sure that the sequencing and the drug responses that have been run against this data is very good. We have about 80,000 drug molecules that have been tested against these cell lines. So you have you run these drug molecules on these cell lines, and then you basically have, for different doses of these drugs, whether the tumor shrank or grew. So that is the other kind of data we have. We have drug pair response of about 100 drugs, so about 100 times 100 drug pairs that have been tested. And then you have databases like Dragon 7, which actually give you the drug composition data, the molecular structure, chemical properties, and there are a bunch of other parameters that you get about the drugs themselves. So you have the information about the drugs, you have the information of the drug response, and you have these different types of cancers that you've run these drugs against. So what's the real problem? The problem really, one of the fundamental problems, and this was alluded to a few times today already, is the feature space is huge. So you only have 60 cell lines, but you have close to 100K features. If you put in the microRNA, the RNA-seq, the proteomics, you put in all of that together, along with the drug descriptors, it basically balloons out into features, too many features. And the question is how to best reduce this feature space. When I first looked at this problem, again, coming from a signal processing information theory background, my first idea was that, mutual information is the best metric to throw at it. And actually, mutual information is at the heart of many, many AI and machine learning algorithms that we do use. But what I quickly realized is you cannot treat anything to do with genomics and healthcare as just number crunching. You cannot treat this as a matrix of 68 rows and 100K columns, and I'm going to just try to reduce feature space. For example, something that happens very often is you run whatever feature selection algorithm you do, and you pick up, say, 20 good features. Some other algorithm will work equally well and pick up 20 features, and they're completely different. So now, why do you say that both of them have, say, maybe, and then you take those features and do your AUC and all, and you get the 95% sensitivity, specificity, all that thing. But now what do you have? You have two very good algorithms that have come up with completely different features. And that is where you really need the biology. You need to look at the gene networks to figure out which of these are actually biologically relevant. So always keep in mind. Again, quickly, these are topics that have been alluded to before. Data curation is a big, big problem in this area. The reason we just work with these 60 cell lines is even though more and more data is coming online, it takes a lot of time to curate that data, make sure it's clean, make sure it's normalized because it's coming from different sources, and that is not easy to do. Data diversity, again, something was alluded to here, is that most of the data we work with for a lot of this is either from the US or some of it is from Europe. Does something that we develop, if you come to a conclusion based on that data, how well does it translate to say, cancer in India or cancer in any other country? Those are big unknown questions that still need to be answered. I'll stop here.
Yeah. As I had mentioned in my initial remarks, I'm just going to be giving a few examples of some of the healthcare and genomic related work that is being done in TCS research. We have a fairly large life sciences group. We also have a fairly large embedded systems research group. And I'll be just flashing a few selected papers that they're just most recent stuff that they've been working on. The larger picture is that there's no picture. Okay, let me just start by just describing my first two slides. I'll describe the first two slides. I think there's a computer change required. So there are two sides to healthcare. One is developing cures, and the traditional drug design pipeline is an extremely long, 10 to 15 years to develop a drug and up hundreds of millions of dollars sometimes to get a drug done. And it's also a very costly cycle, and speeding that up is one very important part of the things that AI can do there, and I won't talk much about that. I think some of the things that Monisha mentioned, and learning from what we have on some cell lines and how can you improve the space search there. The other side of it is personalization and what we now call translational research. A lot of the research is now happening in hospitals because the data is coming from health records and genome sequences, and putting that together, and this is something we're doing very closely with Tata Memorial Hospital and getting this done for specific types of cancer. So I'll just do the two generic charts I have. I'll talk about a few examples now. Predicting the results of the effect of mutations. Now this is very important. I'll give this very specific one first, and I'll describe why it's important. When genes express themselves, they do it via RNA, and RNA sort of has to pick up different parts of the same gene, which are called exons, and then sort of get rid of the middle part, which is called splicing. And sometimes mutations mess up this process of splicing so that genes don't express and the right proteins don't get formed. Predicting when that's going to happen is kind of important
to be able to understand the biology and also to understand how to fix things. Now I'll come to that in a minute. So it turns out that you can, sequence is just a sequence, and deep learning does greatly with sequences. So we're able to now predict what kind of mutations affect splicing and how. This is just a recent paper. But more interestingly, coming back to Sriram's nice description of CRISPR, if you can predict the effect of mutations, you can possibly even predict the effect of beneficial mutations and find them, and then actually execute them. So that's one possible, very promising future line of new types of cures. So that I think that this is probably the most impactful going forward. The other thing is in terms of diagnosis and early prevention detection. Very interesting thing, I'll talk more about it tomorrow. We trained a deep learning model on all kinds of time series from all across, not just medicine, but machines, just speech, all kinds of stuff. It turns out that those features that deep learning model learned was doing better than a model trained on specific data from ECG and EEG, etc. So the model had learned enough time series that it could just work without actually seeing any clinical data. So this is something I'll talk to you more about tomorrow. Very surprising, the whole business of ImageNet, pre-trained models, unsupervised learning. It's very interesting stuff. You can't really explain it too well. Another example is the same thing. We are basically able to do better than and actually get earlier predictions than the best known models trained on the data which they're supposed to predict about. And you train on something else, and it just sort of works. Very interesting and unexplainable. Another thing that this sort of allows one to do is you have data about some disease with good labels, and you have new data. Say a new disease comes out, you don't have data. So because you're able to learn features which are very generic, you can actually use them, it works out, to actually transfer. You don't have anything, because the machine is the same, it's just people, right? The data is the same. But you're able to transfer to a new data set where you actually don't have enough labels, and you're able to do that with less data. So there's a sort of side effect of these pre-trained models in deep learning. They enable you to do transfer learning into areas where you don't have much data. And the last example is from our embedded systems group, where we're working very closely with a lot of our customers who are medical device manufacturers. And they get tons and tons of data, like cardio, of course, and then there are other types of monitors that people have. And they don't know what to do with that data. The algorithm that they have to do, detecting events are, as was earlier mentioned, full of false positives. So reducing the number of false positives so that data actually becomes fundamentally useful to the physicians and to the patients themselves is something that we're currently, basically making that possible with people like, I won't mention the names, but the medical device manufacturers. So we're basically able to get better results. You're really not going to get anywhere until you're in the 95 plus range. So we're still not there yet. But when you get there, you're really doing better than what a doctor would end up doing looking at that data. And so you can actually get predictions from the medical device that you have implanted inside you, which are as good as a doctor. So I'll sum up. Clearly, there are many healthcare and pharma applications, and I think my personal belief is the pharma applications have more long-term benefit. The others are for reducing cost and more efficiency and increasing access, all very good things, but revolutionary changes are going to come from genomics, I feel, right? But there are no shortcuts and there's no panacea. I mean, you can't solve your business model problems, etc., using AI, so you need other things for that. But I think this is the most important. I want to spend a minute on that, or whatever left of the minute, because a lot of people I think a few people have trashed me a bit on this. When I say interpretability, a model which is non-interpretable, which is doing detection and reducing cost is fine. But when the model is making decisions, right? I mean, you're okay if you're able to diagnose retinopathy just better than a human doctor. But if you're going to make a decision as to what you're going to put in your eye based on that, I think you'll think twice, right? And the reason is not that because it's humans or something else. The reason is that when you make a decision, a plane, you can analyze the plane's you can do a formal proof of those real-time systems and think how it works. You need to be able to explain that program which makes that decision. Then one would actually trust that technology. And you don't have to go into the background of the pilot, right? But when it's statistical only, and it's making a decision, I think where, as a society, we're not ready for that today. Yeah. Thank you.
So I guess the panelists can come back to the stage, and the audience can ask all the smart and the pesky and the grandiose questions to our awesome panelists.
While we're waiting for questions, I have a thought. And several people have brought up the question of trust and trust in machine learning versus trust in doctors or other experts, and human experts, that is. And it's worth noting that there's a subfield of machine learning now called trustworthy machine learning or believable machine learning, in particular in the healthcare space. Jenna Wiens at University of Michigan is probably the best example of a researcher that I know anyway who's working in that. And she works with physicians, and the idea is to develop classifiers that produce results that are understandable, meaning you can show why the classifier produced the output that it did. But another thing that I think we should all think about is that if I remember the statistic correctly, the second leading cause of death in a hospital is medical errors, human errors. And so I wonder if we should be questioning the premise that we trust the physician and their judgment, because they often make mistakes. Not just the physician, of course, but all the clinical staff.
But on that point, when Monica talked about who all flew into the, using a plane, I thought she was talking about this, or was also going to talk about this number, that every day, I mean, the number of people that are killed due to human errors is equivalent to two large Boeing 747s crashing. That's the current number, that every day we, on the planet, you lose as many people due to medical errors as the two giant airplanes.
I think there's the other point, which is, I don't think the intent is to remove the human factor when you actually have the AIML. For example, you'll have a public health worker. The message goes through the individual, the human still. Or if you have a diabetologist who's now looking at the eye, the message still goes through them. So the trust is not about where you don't have the human element. I think that's very important in many of these models, not in terms of AI, but models of deployment of these technologies where the human part is not taken out. It's augmenting it.
Yeah, go ahead. You can start, line up there and start asking questions. And make it fast, as in come to it fast.
Hi, I have a question about the diagnosis part using AI. Is there a concern of confirmation bias? Maybe if the app tells me I have diabetes, and I go to the doctor and they tell me, no, you don't, we tested you and you don't. Do I still go to another doctor? Or even the other way around, the physician is not ready to believe that the patient doesn't have diabetes. Is there a risk, and how should AI be used to actually avoid it?
Yeah, this is a risk, I think, in all kinds of decision problems, right? So you have false positives and false negatives. And for each kind of disease or condition, we might want to tune what we want, right? So for a disease like diabetes, it might be good to err on the side of caution and give false positives because there's time and you can always go to the doctor and get a second opinion. If there are other kinds of diseases where we believe care is much more urgent, you might want to give even more false positives, right? So I think that's a trade-off we can, as a research community or in practice, decide. But I think often in medicine, it's false alarms are okay as long as you have some second confirmatory evidence to lead you. What you don't want is an app telling you don't have diabetes, and when you do, and that misses the time you have to probably go to the doctor and get early detection.
But there are things on the opposite side too, because let's say you might think that, let's say, if there's some cancer screening test, that it's okay to have err on the side of having too many false positives rather than missing out somebody. actually somebody pointed out, no, sometimes you want just the reverse. Because wherever you're suggesting that there's a good chance you have cancer, it causes all this agony, and then you have to follow up with a biopsy, which is a very, very invasive procedure. As opposed to if you let this pass, look, the cancer is going to grow, and there are going to be other things, and hopefully soon you will catch that tumor again. So, I mean, it's depending on the specific condition, often people talk about making different trade-offs on false positives versus false negatives.
Yeah,
I
it's the
think-
same, I'm sorry. It's the same issue for all tests, whether they're AI or not.
And I think exactly the real question is that what I have found is even very technical people don't grasp, we are talking about false positives and false negatives as if everybody understands exactly what they are. Most patients don't. And they don't get it that, there is a trade-off, that you cannot always, you cannot be at the 100% on both sides most of the time. And that is a communication issue that I think the medical profession and the technology people need to work on more.
And there's one perspective that I just wanted to add, which is I think any of these technologies cannot be decoupled from policy, from healthcare policy. For example, diabetic retinopathy screening done by NHS in UK, done by, let's say, Singapore SNEC, what they want as outcomes are slightly different. So to a certain extent, on one hand, it's at what's defined from a policy perspective. So the confirmation bias in terms of looking at the AUC and saying where you want to be. One is in terms of we do have these regulators actually specifying where you need to be. So those are well-defined problems, but I think the larger point you're making may be for the others. But in case of diabetic retinopathy, it's well-defined.
Okay. Yeah, hi. Actually on Friday, I'm part of a workshop on wild and wacky ideas in IoT. And I thought I'll come up with one right now, and I just would like your comments on that. So Gautam, you were referring to a lot of ECG and other data. And one of the fundamental applications of IoT today is this concept of a digital twin. You have an asset, and then you have a digital twin that essentially predicts the behavior of that asset. So here is a thought, and Monica, you were mentioning the need for biologists. Can biologists and engineers combine together? After all, whether or not the whole human body is just an electromechanical system, individual parts are an electromechanical system. A heart is an my knee. So can I take, for example, a condition of a heart at a particular instant of time and model it as a digital twin, and then use data that Gautam was referring to, ECG and other data, and then be able to predict ahead? And also going according to what you said, if you look at the genome, a particular set of treatments, how does that impact the future behavior? Does it sound too wacky? I think it's doable,
no, it
right?
doesn't. Actually, again, when I was working back in Philips, there are fairly well developed for just the cardiovascular system, using fluid mechanics, because the cardiovascular system is basically just it's a mechanical pumping system, right? What complicates it is the biology, is the fact that not everybody's cardiovascular system. There are so many other inputs, what kind of hormonal levels you have, what kind of immune system you have, what are the signals your brain are sending. So we do not understand so if you think about anything as a system, right? And if you're an electrical engineer, you want to do system identification, you have an input, you have an output, and then you try to find out what the system is. The problem with biological systems is there are many, many inputs that we don't even understand how they affect the system. And as we go along, we learn more and more about all of the various connections that happen. But yeah, that is the holy grail. And actually, what you were talking about is having this twin. There are concepts of having your own cardiovascular model that you can then use, put in your parameters, put in your current blood pressure, and figure out, what is it going to do in the future. It's not as wacky as you think it is.
Yeah.
I'll add to that. Actually, the key thing that Monisha mentioned is understanding. You need the understanding to be able to have a digital twin. purely statistical digital twins are only a route to the understanding. 20 years ago, or maybe even earlier, there was this paper on arrhythmia where they used a very simple model, a causal model of how the heart pumps and how the electromagnetic system works. And they were able to essentially validate that model with a small amount of data that they had. But from that model, they could generate lots of more data, and they actually could create data which predicted types of arrhythmia which were not already observed. And you won't do that with data. Data science can only talk about what has been observed, right? Even generative models will learn the space which it observes, will not learn a new space. That requires understanding, or that requires a hypothesis, a science.
Just one quick example I would give of work that was done in India, Strand Life Sciences. Many years ago, they had built a model for artificial liver, where they were computationally again simulating and for a lot of the drug design and so on, because I mean, one of the key aspects is the testing for toxicity of these drugs, and they were using computational models to try and. It would be nice to say how many glasses of wine I can have before it gets into cirrhosis.
Okay, we have one last question, and make it really fast.
Okay. Hi, Vijay Raghunathan from Purdue. There's been a lot of talk of interpretability and trust and false positives, but along with that comes the million-dollar question of liability. And I'll pose that a little more concretely. So, for example, Anand, when you go to and sell your tool to a customer, do you need to now provide them with liability insurance along with that, right? In case they get sued because of wrong data or wrong inferences.
So one answer.
I think that's a great question, and I think there are two ways to look at it, and this is actually what we need to do, which is the problem statement that we've looked at is one where for sight-threatening diabetic retinopathy, where the ML needs to be at 100%, we cannot, so the model has to be at 100%. There is no way that you can have a false negative there. So to a certain extent, what you would see in this space with many AI companies, us and others included, is you would need a human to actually continuously verify as you have deployed a certain subset over a period of time before you are able to allow it to be on its own. So that needs to be done. So coming to specifics, we have to take liability insurances for sure. It doesn't matter whether it's India or elsewhere, you have to, because until and unless you are able to prove over time after deployment, training is not enough, single validation studies are not enough. You've got to do this over time before you can actually leave it go.
Okay, so I will summarize in 1 minute or less than a minute.
I think Gautam had a comment there.
I mean, liability or not liability, nothing will prevent you from being sued, okay?
So I think we had lots of ideas in terms of, doing with less data. It's been shown that you can have transfer learning and also pre-trained models working really well. And then you have to think about the disease in the context in terms of, understanding the false positive rates. Artificial intelligence, ML by itself is not sufficient. You need business models. Also, I like the fact that you have augmented intelligence. It's not just artificial intelligence, it's augmented intelligence. I think interpretable modeling is a big thing here. And so side by side, you can reduce the feature space and use domain-specific knowledge in biology to understand some of the feature space. And finally, I like the fact that, you have better observation, finer granularity observation, even at the level of the single cell, where you can understand the heterogeneity in tumors, and better intervention. So can you devise these new models where you have, genome editing at a very precise level so you don't have the side effects. And then I like the wonderful thing that I like, all you healthy people, give your data so we can have these average models for the healthy man. What is the healthy man? What is the healthy woman? The global healthy man. So don't skew the data globally. Don't skew the data thinking that everyone's going to get disease. Think of the healthy people so, we can have this preventative, participatory health for all. With that, I'm going to have, end on a healthy note. Go have healthy food. Banquet is waiting for you, so there's going to be lots of healthy food, so you should rush to the banquet now. Thank you, everyone. That's it for our panel today. Oh, sorry. Don't go without grabbing your gifts. Thank you. Thank you, Amit. Okay. Okay. Oops. I had to do that. Yeah, sure. Networking, small networks.